Good morning, everybody, and a warm welcome for IHPBA opening day. This session is a miscellaneous one on different topics, bit of rescheduling, and I would request Professor Ghoshal for the first talk, statistics for the novice. I think as a surgeon, this is a very common phenomenon that statistics is a bit of novice for everybody of us. So, Professor Ghoshal, um, he doesn't need any introduction in Kolkata. We are lucky to have him in Kolkata after his retirement from prestigious SGPGI. And he's a senior consultant gastroenterologist and luminal gastroenterology motility Institute of Gastrosciences and Liver Transplantation in Apollo Multispecialty Hospital. And we all know he was a professor and head of the Department of Gastroenterology in SGPGI Lucknow, from where after retirement he has come to our city. Professor Ghoshal, your talk, please.
Yeah. Can I have my slides? So thanks for the nice introduction, and it is a privilege for me to talk on this unusual topic to a gathering of surgeons. But let me tell you, this is very, very important. I know how much work surgeons do because we gastroenterologists started trying to become the surgeon. So we know how much work surgeons do. But all your work remain local and it doesn't become global. You know why? Because if you don't know how to keep the data, how to analyze the data, and how to publish, what happens is the work that you do remains local. Second thing is, if you want your work to survive beyond we are not there, then you need to understand statistics. And I tell you, statistics, in my opinion, is much easier to learn than surgery. So I'll try to give some introduction to you. I'll not bore you. And at times I will be interactive. You stop me wherever you want. And the next thing is I will also do something using software so that you can see how things are done. Now, the learning objective of this presentation is to learn or recapitulate, because some of you might be doing all this, so I want to recapitulate for them. Those who are not doing it, to learn a few basic statistical principles on data analysis, to learn what hypothesis to apply to your data, and to learn doing a few simple statistical analysis on your own. Now, if you want to know more about, you can read this chapter that I wrote quite some time ago. And if you want to download this chapter, go to this teaching website that I use for teaching, which is www.biomedinfo.net. Okay, now let me tell you, when you do a research project, what do you really need? What you need is first conceptualization. And some people have God-gifted brain. Many of us, we don't have. So, like this man, Newton, thought, why apple is falling from the tree? Why it is not going up? And he discovered gravity. Okay? But those who are not born with that kind of mind, curious mind or original mind, the best way to learn a question or ask a question on research is to become scholar. To listen to the people who regularly do research, because many a time while passing, they tell there is no data on this, and then capture that and start your work. Now then you need to learn how to design a study, how to get funding for the study, how to manage the fund, how to execute the study, and subsequently how to analyze, publish, write the paper, then marketing the data. That means you publish something, you have to market globally. This is how big scientists in many developed countries, they become world authority. So I'm not talking about all this. This is totally like an MBA. it requires a lot of management. But I'm going to talk about little bit data analysis. So I'll present what are the types of data, distribution of the data, and what is normal distribution, what is null hypothesis and alternative hypothesis, how to choose statistical tests for your data, concept of p-value, and concept of univariate and multivariate analysis. Let us look at this data. This will be either in an Excel sheet or maybe in an SPSS sheet. It will depend upon what software you are using to analyze the data. You can see here, age of people are presented, gender is presented, and you can see there, gender is not written as male and female. It is written as 0 and 1 with a definition above. 0 means female and 1 means male. Don't take it otherwise. It could be reverse also. 1 can be female and 0 can be male. Now why? Because statistical software do not understand text. So therefore we convert the text into a number. Now subsequently you look at, this is Harvey-Bradshaw score, which is used for severity assessment of Crohn's disease, and you have some laboratory parameter such as hemoglobin, serum albumin, fecal calprotectin, and then you have something like whether the patient responded to a medicine. If responded, it is 1. If not responded, it is 0. Whether somebody required biologic, 0 and 1. Now, can somebody tell what is the type of data? This age is what type data? Anybody? What is type of data for age? Very good. Very good. Continuous. Now somebody else, what is the type of data here? The gender. What is the type of data when I talk about gender? 0 and 1. This is categorical. So what is categorical? Categorical means nominal because it refers to a name, whereas continuous also is called scalar. Scalar means it has a specific scale. So there are two types of data, categorical or nominal or discrete, because categorical cannot be in decimal. Like age can be in decimal, 24 years, 3 months. This is a decimal data. So that's why it is called continuous data. Whereas categories are category, either male or female. So in the world there are two types of data, categorical, nominal or discrete, and continuous or scalar. Now there is one other type of data. Can somebody tell me what is this type of data? Harvey-Bradshaw score. It is a disease severity score. Looks like a continuous data. Yeah? Yeah, very good. So I know these are very good thinking surgeons. They are all thinking surgeons. Very good. So this is ordinal. Because we have kept this data artificial in order, because if somebody is Harvey-Bradshaw 1 and somebody is 3, so the difference is only 3. But another fellow can be Harvey-Bradshaw 3 and another fellow can be 6. 6 and 3, the difference looks like 3, but it could be more severe. So this is artificially an order created. That's why we are talking about ordinal data. So data are either continuous or scalar. Same, continuous, scalar. These are two names for one type of data, categorical or discrete or nominal. And third category is order, which superficially would look like continuous data, but it is artificially created order. Now, look at this. When you present the data, you don't send to the journal the master chart. You have to analyze. It is like when you buy vegetable, you don't give to your guest the raw vegetable. You have to cut, you have to make their shape, you have to cook, and then it has to be palatable. Similarly, when you give to the journal, it cannot be the only master chart. It is, you give central tendency of the data and dispersion of the data. I've seen many authors, they present only central tendency and not dispersion. This is meaningless. So what is central tendency? Central tendency can be mean, median, and mode. Mean, median, and mode. What is mean? Mean is arithmetic mean. That means you just add up everything and then divide by the number of patients, that becomes mean. Look at here, the mean is 15 years. So if you present to me, the mean of your study population age was 15 years. To me, these are adolescent people, maybe pediatric people, because now pediatric cutoff is 18 years. So as a reader, I know you are talking about a pediatric population because your mean is 15. But look at the median. Median is different. I'll tell you. Look at this. There is an outlier. This fellow is a 98-year-old and all others are 6, 13, 11 years old. So all are pediatric population, but there is an outlier who is a 98-year-old person which has pushed the mean to 15. And if you give me only mean here, I cannot understand because you have not given me dispersion. Dispersion means either standard deviation or range. That will tell me there is a fellow who is 98, so I have to look into the data carefully. This is not a pediatric population. Look at the same data. I have calculated the mean, okay, 5.5. Now let us look at the median of the same person or same group. The median is reflecting the data or central tendency better than the mean. So that means this is not a normally distributed data because there is an outlier and here using mean is useless. So any data which is not normally distributed do not present mean. You present median. Median means you put the data into ascending order or descending order and take the middle value. Okay? And if you have used mean for central tendency, do not give range. For mean central tendency, you should give standard deviation. So what is standard deviation? I will not get into. This is square root of variance. Square root of variance, but I don't want to explain that here. So what happens is that if your data is like this, do not present mean, present median. If you have presented median as the central tendency, your dispersion will be range and not standard deviation. Because standard deviation also get affected by outlier. Now let us come to next. So this is dispersion of the data. It can be range or interquartile range. What is interquartile range? If the range is too big, for example, let us say 1 to 1000 is the range. So it is a bad range. I can't make sense out of it. So what you do is that convert this data of 1 to 1000 into quartile. Quartile 1 means first 25%, quartile 2 second 25%, quartile 3 third 25%, quartile 4 fourth 25%, and then take the first quartile end, that is 25%, to third quartile end, that is 75%. So that is called interquartile range. So when the range is too wide, we present interquartile range, otherwise range is fine. Okay? Now why this is important? Because this is important because what you are trying to do, you are trying to study a population, maybe 100 people, maybe 200 people, maybe you are trying to see outcome of acute cholecystitis 200 patient in your hospital. So why a journal should publish this? Why we should read it? Because you are trying to say that what I saw in 200 people would be happening in the whole world. So your population is this much and you are trying to derive a conclusion from that population to apply to the whole world. That's why journal publish it. That's why you will all read it. So question is, if your population is skewed, what will happen? Let us say I do a study, what is the average income of people of India? So I take this population and ask you, what is your monthly income? You give me the data. And then I make an average, maybe mean with standard deviation or median and range, and I say that average income of people in India is maybe 5 lakh a month or 2 lakh a month. Is it acceptable? Not, because this sample is not representative of whole India. This is a skewed sample. So this is not a normally distributed sample. So what is normal distribution? Where you present the data and then you find beautifully a bell-shaped curve is made. I'll explain to you that curve. But simply, if you want to know whether the data is normally distributed or not, calculate the mean. Calculate the median. and see, are the mean and median very close? If they are very close, the data are normally distributed. If the mean and median is very widely different, data are not normally distributed. I gave you an example where an outlier of 98 pushed the mean to 15 years age, but when I removed the outlier, the mean was 5 years. So this is a widely different mean and median. The data are not normally distributed. These are skewedly deviated data. So this is the reason why we do that, because we are trying to do a sample study, and the sample is suggestive of the whole population, and that's why it is important. So what is the practical meaning of this? If your data are not normally distributed, use non-parametric statistical test. Whereas your data are normally distributed, use parametric statistical test. Why? I can show you a p-value which you made significant by a parametric statistical test. I use non-parametric, it will become reverse. Because parametric statistical tests are less powerful tests than non-parametric. So therefore, if your data are not normally distributed, use non-parametric. Data normally distributed, use parametric. So let us look at this. Therefore, if I recapitulate data, nominal, categorical or discrete, continuous or numerical, ordinal and scalar, if this is scalar data, non-parametric or parametric. If normally distributed, this is parametric data. If this is not normally distributed, these are non-parametric data. How will you know that whether parametric distribution is there or not? Very simple. That you look at the sample size. If sample size is big, often the data are normally distributed. If the sample size are small, often the data are non-parametric or not normally distributed. Second is calculate the mean and median. If mean and median are very close, the data are normally distributed. If mean and median are very widely different, the data are not normally distributed. We use a statistical test to check that, but I am not trying to crowd your memory with all those difficult names. Now, what is odds ratio? In many journals, you listen to this term very often, odds ratio. And they will talk about 95% confidence interval. What is odds ratio? Odds ratio is, let us say 10 people, you had surgery and 2 died. So 8 survived. So what is the proportion of who survived? 8 out of 10. But what is the odds of who did not survive? Or what is the odds of surviving? This is 2 out of 10. Because if proportion who survived is 8 out of 10, then odds of surviving is 2 out of 10. Okay? Let us say another group, 10, you did not do surgery. And in them, let us say 3 survived and 7 died. So what is the proportion of death or survival? It is 3 out of 10. What is the proportion odds of survival? It is 7 out of 10. So what is odds ratio? Odds ratio is ratio of odds of those who underwent surgery, ratio and those who underwent surgery. That is odds ratio. Okay, that is odds ratio. What is the meaning of this? Meaning is, if odds ratio is 1, surgery has nothing to do with survival. If odds ratio is 1, means the 2 groups survived or died equally, so there is no point of doing surgery. If the odds ratio is more than 1, then surgery is useful. And if odds ratio is 3, means there is a 3-4-fold greater survival if you did surgery. If odds ratio is 10, means there is a 10-fold greater survival if you did surgery. On the other hand, if odds ratio is negative, below 1, let us say -2, -3, that means surgery is lethal. Surgery is killing them more. So this is the concept of odds ratio. And what is the concept of 95% confidence interval? Very simple, I tell you. If you have done a study and in that particular study you found an odds ratio of 5. Now this is one study. It is not that the one study is done exactly the same will happen every time. If you do 99 more studies, what will be odds ratio in those 100 studies? What will be the range of odds ratio in those studies? So that means out of 100, 95 studies, if it shows odds ratio is between 2 to 9, means 95% confidence interval 2 to 9. That means if I do this study 100 times, actually 95 times, I'll find a odds ratio which suggests that surgery is useful, and it ranges from 2 to 10. Is it clear or not clear? Anywhere not clear, please stop me. Okay. Now we go further. Let us see how we do odds ratio. Very simple. This is a software that you can use. This is called EpiInfo. This EpiInfo comes from CDC, Center for Disease Control, Atlanta, Georgia. This is free. You don't have to pay. Okay, so this, when you open EpiInfo, this is what you see. Just click on StatCalc. The moment you click on StatCalc, a lot of things will come. You can take one. Let us say I take this table 2 into 2 into n. So the moment I do that, this is what comes. So this is what I'll write, what I just told you now. 7, 8. This is what I said 3, and this is what I say 7. Now look at this. It gives me chi-square, which I'll be talking about later. But look at this. It gives me odds ratio. Odds ratio is 0.5. That means whatever intervention we did, it is protective. Okay? 0.5. Okay? And look at the 95% confidence interval from 0.07 to 4.5. Is it clear? So this is so simple. Once you practice a little bit, you will be all able to do, and then you can make meaning out of data, and you can even publish. Okay, now let us go to, we have already shown you odds ratio. Now, look at the hypothesis test. Do you want me to talk about sample size? I think my time is not much left, so I'll skip the sample size for the time being. Maybe I'll come back later if I get time. Now, let us look at hypothesis test. What is hypothesis test? When you begin a study, you have a hypothesis. What is the hypothesis? Let us say I take patient who has pain abdomen and McBurney's point shows tenderness. And now I say I do surgery in some of them, I don't do surgery in some of them. It is a randomized controlled trial. Obviously today nobody will do this trial, but let me take an example which is very surgical. Now what happens is your hypothesis is surgery will save patient life, surgery will reduce morbidity. Am I right? Am I right? Okay. Now my hypothesis, I say surgery will be helpful. What is the alternative hypothesis? Surgery is not helpful. Surgery is not helpful. So this is the question. The question is, the study hypothesis or study question is surgery is useful. Null hypothesis says surgery is not useful. Okay? So this is alternative hypothesis. Alternative hypothesis. So your hypothesis and this same hypothesis. Okay? That is alternative hypothesis. Now we have to nullify this null hypothesis. We have to nullify this null hypothesis. How to nullify the null hypothesis? Very simple. If I am correct 96% of the time, then the mathematician has said a rule that then your hypothesis is taken. Okay? Whereas if I am incorrect more than 5% of the time, then mathematician has set a rule, null hypothesis is correct. Am I right? Clear? So how to do that? You are saying 5. That means out of 100, if 5 times or more than 95 times, that means less than 5 times, you are correct, then null hypothesis is rejected. So out of 105, so out of 1, 0.05. That is p-value. P stands for probability, and the probability is that less than 5 null hypothesis was correct. So out of 105, out of 1, 0.05. That is the concept of p-value, and this is a rule set by mathematician. Now, so then how will you do that p-value calculation? If your data are nominal, categorical and discrete, it is chi-square test or Fisher's exact test. If your data are categorical, nominal or discrete, it is chi-square test or Fisher's exact test. If your data are continuous or numerical, look at whether the data are ordinal or scalar. If it is ordinal, the method is Mann-Whitney test or Wilcoxon sign rank test. Sorry for the difficult names. Okay? But if your data are scalar, that means continuous, then it is paired or unpaired t-test. Don't say unpaired t-test, some people say student t-test. Do you know what is the history of student? Student history was one fellow who used to work in alcohol farm. And he used to test which alcohol is good, which is not so good. And then he derived a formula. He calculated the p-value. And then says, I can tell this alcohol is good or bad. And he wanted to publish this in his name. But alcohol company says, you have taken salary from us. And while your work you have innovated, so it goes in our name. So he did not agree. So therefore, it is published as by a student. So he said, I am a student, I always want to learn. So he could not give his name. And that's why it is called student t-test. So now we do not use this term student t-test because it is used by teacher, it is used by student, it is used by everybody. We would love if we could take his name, but we can't take his name. Okay? So this is paired or unpaired t-test. So Mann-Whitney U-test is for unpaired data, whereas Wilcoxon sign rank test is for paired data. Paired t-test is for paired data, and unpaired t-test is for unpaired data. I will tell you what are these paired, unpaired later. Okay? Whereas ordinal data, I told you, this is an artificially ordered data. Therefore, we need a very powerful test which is in favor of null hypothesis. That's why you will always use something like a non-parametric test. Has it started boring you now or no? Anybody who gets bored, please raise your hand. I can't find anybody. I can't believe these are all surgeons. Thank you so much. So parametric and non-parametric test I have narrated. I'll skip this chart. I'll also skip this chart. Now in chi-square test, I'll show you how it is done first because surgeons usually like action. So that will interest them more. Now look at this. When I use this, I gave on this side 2, this side 8, this side 3, this side 7, and you can see, you can get here the chi-square test. Can you see? This is uncorrected chi-square is this much, and p-value two-tailed is this much. This is corrected chi-square is this much, p-value is this much. And this is Fisher's exact test. Fisher's exact test is as good as corrected chi-square. This is this much. Can you tell me from this two-tail p-value says 1. 1 is the p-value. What does it mean? Not significant. So what is the probability? Null hypothesis is correct. How much is the probability null hypothesis being correct? 1 means 100%. So we have sort of got defeated very badly by that null hypothesis. Okay. So you saw how chi-square test is done? Okay. Now what happens is when you do chi-square, if your sample size is too small, then you have to do either Yates correction. Yates is the name of a person. Okay, he discovered this as a mathematician. Sometimes people say there is no need to do Yates correction, just accept the Fisher's exact test. So Fisher's exact test is like Yates corrected chi-square test. Okay. So can you do chi-square now? All can do? Yes? Do you want me to show once more or no? You want me to show once more how it is done? No. Yes? Who says yes? Okay. So I'll show you if I get time. So comparison of the two continuous variables. Till now I was talking about categorical variable. Continuous variable, I told you. Unpaired t-test, this is parametric, whereas equivalent non-parametric is Mann-Whitney U-test. Paired t-test, equivalent non-parametric is Wilcoxon sign rank test. And if these are only possible if your variables are two, you are comparing X versus Y. If you are comparing X versus Y versus Z, then you have to do one-way analysis of variance or Kruskal-Wallis H test. One-way analysis of variance is parametric test, Kruskal-Wallis test is non-parametric test. Fine. So you'll get all this in that chapter that I shared with you. So what is the concept of paired and unpaired? The concept of paired and unpaired is, if you are doing a case control study, these are unpaired. For example, you want to see height of boys and height of girls. So obviously they are unpaired. Whereas if you see blood sugar value before, let us say, insulin and after insulin, the same person is working like his control, so there it is paired. Should look at your data and see which is paired and which is unpaired, and accordingly you select your statistical test from this that I showed you. Yeah, this one. Okay? And you have to remember only 2 PowerPoint slides. So in your front of your study table, you can put this slide and the first flow chart that I gave you. And then try doing your statistical test yourself and not go to a statistician. Sorry for the statistician, but we have to all do, because surgery is more difficult to learn than using statistical tests. That's why we are trying to do ourselves. So question is now, let us go to this. Whatever till now we have done, these are association. But association does not prove causation. Okay? It is like if suppose you find that people who are obese are more often diabetic than people who are non-obese. Now you cannot say obesity causes diabetes. The reason is that maybe those who are obese, they walk less. Maybe those who are obese, they take more food, eat more. Maybe eating has caused it. Maybe those who are obese, they have a gene which is for obesity, and there is a disequilibrium with another gene which is diabetic gene. Okay? So that's why they get carried together when crossover happens during meiosis. So therefore we cannot infer that obesity causes diabetes. So this we only say there is an association between obesity and diabetes. Mathematically, if I have to infer causation, then I have to look at correlation. Is it there is a linear correlation between weight and blood sugar value or HbA1c value? That is one. Second, I have to do multivariate analysis. I have to factor in obesity, genetics, amount of calorie intake, presence of, let us say, how much exercise they do. And then with all these factors, I do statistics together, and that is called multivariate analysis. So how to look for correlation? Correlation, again, for parametric data, there is different. Parametric data, you do Spearman's rank correlation. Whereas for non-parametric data, you do Pearson's correlation. So Pearson's correlation and Spearman correlation, depending upon whether your data are parametric and non-parametric. How does it look like? Look at this. This is called scatter plot, where the x-axis, let us say, is a weight, y-axis, let us say, is HbA1c, and you find that as there is an increase in the weight by 1 kg, there is an increase in the blood sugar by a specific unit. So this is a beautiful positive correlation. This is a negative correlation. Negative correlation. Let us say I say that obesity and let us say coronary artery diameter, and you find those people who have obesity, they have narrower coronary because of the plaque. Now there, it is a negative correlation. As weight increases, coronary diameter decreases. And this is no correlation. Okay? And this correlation, you typically use a statistical test, Spearman correlation and Pearson's correlation. Okay? Now this is the multivariate analysis. Till now, whatever I spoke about, these are association. They do not prove causation. It is like 5 men went to saw an elephant and everybody had an inference. These are association. Okay? But what you have to do is you have to do something like this. First, you do an univariate table and see which factor are significant. Which factors are significant. Then take all those factors which are significant and put in a multivariate model. Typically, I often use a model called stepwise logistic regression model, and look at which are independent factor associated. Obviously, I will not be able to talk or demonstrate you here, because from you, some people may be interested, and then gradually as you climb up the ladder to do more statistical tests with data, we can take an advanced sort of presentation like this, where I can present to you multivariate analysis. Thank you so much. Any question, I will love to answer.
Uh, Thank you, Professor Ghoshal. I think the discussion and question answer is at the end of the session.
Oh, this is done?
Yeah.
Thank you.
Okay. Please have a seat here.
Thank you.